So now that we've got a more sophisticated set of tools at our disposal, we can start talking about more complicated forms of probability. Namely, when we were examining the contingency table in the previous video, we had information about the different combinations of A and B and A bar and B bar. And what we're going to rely on now a little bit, if I can jog your memory, is we're going to be using some prior knowledge to inform our probability calculations. So if this sounds like this is moving into the subjective interpretation of probability, we kind of are. We're using this prior knowledge to inform and update our estimates about the likelihood of an event. So formally though, let's talk about the conditional probability of an event given we know another event has occurred. So conditional probability is calculated, and we would read this statement here as the conditional probability of A given B has occurred. So it's not the probability of B, it's the probability of A, but we've updated it now that we know that B has occurred. So really the interesting part here is the A, and then this part is just telling us what has already happened. So that bar is just indicating this is the condition that we're adding on to what we know about A. And we calculate that as the probability of A intersect B divided by the probability of B. And one quick way of thinking about conditional probability is, and I'm going to go back to a Venn diagram perspective here. Imagine you have your sample space here, and you've got A, and you've got B here, and you know that B has occurred. So, reminder, that's B, that's A. When we know that B has occurred, what we're essentially doing is we're collapsing the sample space to just being B. So we now no longer care about everything outside of B. So now we're excluding that from our sample space because there's nothing random about it anymore. It's been determined. So now this is A, or the portion of A that's in B. So now instead of shading A, right, what we're saying is the conditional probability of A now is going to be this segment here, this segment here out of the total sample space that we have now, which is B. So that would be out of all of this. So it's like rescaling. We're ignoring everything that happens outside of B. So let's return to our example to see what we mean here. So we had a contingency table for the sample in which 200 people were asked whether they use menthol e-cigarettes or not, and then 2 years later tracked to see whether or not they had developed lung cancer. So our question now is, what is the conditional probability? And sometimes we may skip the word conditional and just say given that, and these are interchangeable ideas. Given that a randomly selected subject has lung cancer, given that we know that they used e-cigs. So if if we're trying to read this, so the probability, right? We're interested in a probability. A randomly selected subject has lung cancer. So that's event B. Given we know that they used e-cigs, so given the certainty of event A. In other words, what we're asking for is we're asking for the probability of B given A, which we know then that will be the probability of B intersect A divided by the probability of A. So everything that comes after the bar in the initial statement here is what's going to give us our denominator. So in context, what we're saying is, out of the people who use e-cigs, how many of them developed lung cancer? So since we're eventually going to be talking exclusively about cardinalities, what this reduces down to is the number of people who use e-cigs is going to be the denominator, and then the numerator will be of those who developed lung cancer. Okay, so ignore all the outcomes in which A hasn't happened and only care about what happens inside of the event A. So if we go back to the contingency table, I'm going to write it down again. So remember what we had was A and A bar and B and B bar. We had our row totals and our column totals. And our grand total is going to go in the corner there. So when you're setting these up, you don't have to be super, super neat, but it helps to have a little, some amount of neatness to make this work better. I'm literally just copying down the contingency table we had before. And so when we say the probability of B given A, so what we're going to do is we're going to ignore everything that isn't A. So this row right here does not matter to us, neither does this one. We're only going to look at the row that includes A. So we're going to take the cell for A intersect B, or B intersect A, however you want to write that. The order doesn't matter here. And we're going to take that out of the A row total. So in other words, we're looking at 19 out of 45, which, if you want to write that as a decimal number, 19 divided by 45 is approximately 0.4222. Remember, 4 places after the decimal if you want to be precise. And we're gonna stick to that. So why is this helpful? So if we're using conditional probability, we actually are going to gain a lot of information about how events relate to each other, and whether the occurrence of one event affects the probability of that event. So in other words, this is the probability of B given A, but remember that the probability of B itself, so regardless of whether A has happened or not, this was 23 over 200, which we said was 0.115. So in other words, it appears that conditioning on A, right, whether A has happened, so whether or not you have e-cig, whether you're an e-cig user or not, has significantly changed the probability of developing lung cancer. So In other words, if we wanted to interpret this statement, while the baseline rate of developing cancer, lung cancer, remember that's what we were saying, that was prevalence, right? Point prevalence. Point prevalence. Spelled that wrong, sorry. Well, the baseline rate of developing this lung cancer is roughly 11.5%. Among e-cig users, at least in this study, this rises to 42.2%, which is a significant jump. And that's what conditional probability is telling us. And we're going to formalize what that means in a future video.